All right. Hello. We're just going to do a little review of summation notation. Um, just sums in general, information you need to know. So this is relevant to like the Math 101 and at UBC, or really just integral calculus in general, first year typically. Um, because you start talking about integrals, define integral as the sum of various terms. Even later on in the course, you will talk about just actual sum or like discrete sums, you call it, which is uh, if I add um, like an infinite number of terms together, in some occasions that can actually equal something. Like the a kind of famous example is an example of like one over two plus 1/4 plus 1/8 plus 1/16 plus on and on and on, following in that pattern, right? Just a half of the previous. It is an infinite sum of positive terms, so um, perhaps we just think that that this doesn't that this might not mean anything, that this won't equal a particular number. Um, uh, but it can be shown to, in fact, equal one. The like kind of typical way you might explain this. It also falls on it. This is what is classically called Zeno's paradox. It's this idea that imagine you were on a racetrack that went from 0 to 1 uh, meters, kilometers, I guess, whatever the unit of measurement is. Maybe just 1 represents the finish line, 0 represents the start. Uh, we can understand uh, the sort of progression of your position in the race as, oh, at some point you are halfway through the race, and at some point after that you are half of the way, so you are a quarter of the way through the race, and at some time after that you are half of that, or you are half of what was previous, yes, or 1/8 of the way through the race, through that section, and then 1/16th, and I can keep subdividing the remaining distance into a half. Uh, and so we can sort of understand the progression of going from 0 to 1 as the summing up of all of these sort of halves 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 of halves, to be one. That um, I am, in some sense, going halfway and then halfway again and then halfway again and then halfway again of what's left. And this we understand that we should finish the race. It's called Zeno's paradox because like the in classical times people would have said, like, or there was an argument people made that how can we possibly finish the race if every time we're still have half of the remaining distance to go. But of course we understand we can finish races. It has to do with the fact that the the time it takes to complete each new half of a half of a half, whatever, um, the time it takes to do that also shrinks, and it shrinks at a sort of an appropriate rate so that the total times don't just blow up to infinity. That I don't just take infinite time to complete a race, right? Um, so later on in integral calculus, you will deal with these sorts of discrete infinite sums. Sometimes they may converge, sometimes they may diverge. But just getting into the basics here, we want to understand summation notation, understand some key ideas involving sums. So summation notation is this little guy, capital sigma. I'll just write an example, say like n equals let's do like 3 to 6, maybe something like that. Uh, Maybe this is n squared plus 1, let's say. Just again, a pure example. So what we talk about here, what we can label some things as is The n is what's called the index of the sum. It sort of keeps track of what term in the sum we're talking about, and also influences the form of terms. Um, the bottom number next to it is your starting value or your starting index. The n value starts at that value. It progresses by one until it hits the ending value. This value you have uh, at the top. Um, and the thing next to the uh, capital sigma, this notation, is the form of the terms. Um, that each term will look like that, uh, in this case, dependent on n. So what I should get from here is uh, this will have an n equals 3 term. It will have an n equals 4 term. It will have an n equals 5 term. And it will have an n equals 6 term. Again, start at 3, go to 6 in steps of 1. And the form of the terms, again, are given by in this case, the n squared plus 1. So I say, all right, what if n is 3? Well, then 3 squared is 9, and 9 plus 1 is 10. So this term is 10. Uh, if n is 4, we have 4 squared, so 16, and then 16 plus 1, so 17. If n is 5, we have 5 squared, so 25. And if we add 1, we get 26. If n is 6, then n squared is 36. And if we add 1 to it, it's 37. So that's the form of those. And I could add them up and say, oh dear, what? 10 and 26 is 36, and 17 and 37 is 54. And together they are 90, right? And so that this notation in this case represents this term 90, although it really is more, it's not about it just equaling 90. It's more about it representing this sort of um, summing up of terms in this particular way. And yeah, okay, it's not like terribly useful in this case. It wasn't a whole lot of terms. I could have just written them out individually, but the power of summation uh, comes when you have to deal with summing up many, many, many terms, hundreds, thousands of terms, let's say. Uh, then you probably don't want to add up each individual term. And if you find a way to write it as a summation, you can take advantage of summation formulas to tell you what the value would be in a much simpler manner. Um, and then also this will enable us to talk about sort of infinite sums. Again, this is important for these sort of infinite discrete sums like the Zeno's paradox, as well as talking about integrals. Because when you're defining integration, you're going to define it in terms of like adding up many, many, many areas underneath the curve, rectangles, I suppose. You'll typically start with, general. So you need a way to write these sums. Yeah. Um, Now, I said we have some summation formulas that we may take advantage of, and some summation properties. A couple of our properties that we could say are the summation, and sometimes too, you might see just nothing written on the top and bottom, or maybe just like an n written on the top and bottom. In these cases, it may be supposed to be clear what the index is, or what the summation variables are, or what the index starting values and ending values are, or maybe we just don't really care and it will apply in any case. That's what these properties that I'll write here. I don't care what the starting index is. I don't care what the ending index is. Uh, um, these are just generally true things about summations. So one thing that is true, if you have a constant multiple times something that depends on n, and generally when you talk about sums and series is just or sorry, sums and sequences. Remember, sequences is a list of terms, and a series is a sum of terms. So a series is like a sum of a sequence, kind of. Um, you'll see often this sort of subscript notation like A of n. Um, that's to suggest that uh, that value changes as n changes. In fact, we could also write this as functional as sort of a function notation as just like A of n. But you'll see this sort of subscript notation more often, and then you'll see things like say like A of one is perhaps the first term, or maybe A of zero, or A zero is your first term. If you're a computer programmer, you probably count from zero rather than count from one. Or if you're just a computer, I don't know why I would be talking to a computer. Well, I am talking to a computer. Anyways, that if I have a constant multiple times something that depends on n, so I'm implying here that this C does not depend on n. It could depend on like other variables, but it can't change with n. Um, that if I have this, the C can come outside. I can factor out anything from the anything from the summation that doesn't depend on n and is multiplying terms like this. That's one property. Another property is that um, sums distribute over products, or sorry, over summations distribute over sums or differences. So if I have a sum or difference of terms inside the summation like this, it can sort of distribute, and I can talk about the sum of each individual uh, term like that. Um, um, Notice that it is not true. You cannot distribute the summation over like a product. If I had something like the sum of an times bn, I can't write that as like the sum of an times the sum of bn. That would not be true in general. But that should kind of be clear. Again, some like sums are just generalizations of just addition. So like if you even thought that that was true, um, it would be like saying if I had 1 times 2 plus 3 times 4, that would be equal to like the sum of the first guys, so like 1 plus 2 times the sum of the second guys, 2 plus 4. But that's not true, right? This would be 14 on this side, and unless we were terribly lucky, this right-hand side won't be equal to that. And of course, it's not. It's 4, 6, it's 24, right? So sums can't distribute over products or quotients, but they can distribute over, well, sums and differences. Um, you also have some summation formulas that you could use or that you need to be aware of. Um, here they are, that if I sum from n equals 1 to big N, so in this case, I actually have a capital N number of terms. Another common mistake is students thinking that the top piece of the summation is how many terms there are, but that's not always true. It depends on where the starting index is from. Right? When I did the 3 to 6 one, there wasn't 6 terms. There were actually 4 terms. There was a term for 3, a term for 4, a term for 5, a term for 6. There were 4 terms, not 6. Um, I suppose you could generalize that to be if you do the top index minus the bottom index plus 1, that's how many terms there are. The top index minus the bottom index. Um, but one of our summation formulas is if you sum the constant 1 This one should be obvious. If I sum up one capital N times, I just get capital N. 1 plus 1 plus 1 three times is 3. 1 plus 1 plus 1 four times is 4, of course. Right. So that's like our simplest formula. We have n equals 1 to big N of little n. So this is like a sum, in this case, of like 1 plus 2 plus 3 plus 4 plus 5 all the way up to capital N. Uh, this is a fairly famous one. I believe Euler was the first one who uh, derived this. I heard it was like a classroom story that the teacher wanted them to sum the numbers from 1 to 100 and to kind of kill time. Uh, and the Euler found found this formula to do it much faster. And the story goes the teacher got mad because it didn't take him very long. But anyways, this formula is n times n plus 1 over 2. I won't go into the derivation right now for time, but that's 1. We have the sum from n equals 1 to big N of n squared. This is the one I always summed, or I'm never as confident with this one. I will check in just a moment, but I think this is it. It's what my brain is telling me. Let's just make sure. Da, 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 da. That is right. Yeah, that's our formula. We also have one for n cubed. This one I like because it is essentially just the n formula, um, except squared, like this, right? Um, those are some formulas that you commonly see to break down sums. Um, and then there's one final one that we do need to cover just to make sure. It's called, usually this one starts, well, depends how you write it. I guess let's do 1 to n. Maybe we'll keep it simple like that. And it's AR to the n minus 1. This is a geometric sum. You might remember from like elementary or high school, you would have learned about what are called arithmetic sums or sequences and geometric sums and sequences. Arithmetic sums and sequences have a common difference between the terms. So if I always add to get to the next term, if I always add the same thing to get to the next term, then it is arithmetic. So like 2, 4, 6, 8, 10, 12, 14, I'm just adding 2 each time. That's an arithmetic sequence. Geometric was when when you multiply by the same thing over and over again to get to the next terms. Geometric sums are, in a sense, more useful, or you'll use them more. You don't really do much with the arithmetic because infinite arithmetic sequences are not very interesting. If you keep adding the same thing over and over, or subtracting the same thing over and over, same basic idea, your terms just they just grow unboundedly, either in a positive or negative direction. And so like the sums won't converge to anything unless you have a very particular arithmetic sum of just like zeros, I guess. A bunch of zeros is just arithmetic, I suppose, with like a common difference of 0. Whereas geometric sums, like you saw with the Zeno's paradox, that was geometric because that was basically multiplying by 1/2 each time. I start with 1/2 and I multiply by 1/2 to get the next terms. Geometric infinite series rather, can converge. And so these are much more valuable to us. This has a formula. It's A times 1 minus r to the big N over 1 minus r. Often you could try to write like your geometric sums into this form, and you can tell what the A and the R are. But also the A is just the first term in the sum, and the R is the ratio, is that common ratio. So if you knew that a series was geometric, you can just look, oh, what's the first term, and just divide, say, like the second term by the first term to get the common ratio, right? Um, and then once you have A and R, and then capital N is just how many terms are in the series in this case. Um, if you know these, then you can just plug it into the formula and you can get your result. And then there's an infinite sum result where if n goes to infinity, if big N goes to infinity, and if r is less than one, then something less than one to the power of or to power of n as n goes to infinity goes to zero. And so you just get basically a over 1 minus r. But that's only under the condition that the absolute of r is less than 1. Okay. Right. Let's just do a little showcase here of using these rules, as well as a bit more of another idea for summation manipulation. Um, let's say I had uh, this. Hmm. Yeah, actually, let's do this. Let's say n minus uh, 2 squared. Okay. Say I have this sum. Again, it's not like terribly large. There's only 5 terms, so I could just calculate it myself, but this is just a demonstration of the idea. Uh, if I wanted to calculate this with the summation formulas, uh, the sort of straightforward yet tedious approach would be to expand this as like n squared minus 4n plus 4, and then distribute the sum onto each term. You would have an n squared term, you have an n term, and you would have like a constant term like 4, or like 4 times the sum of a bunch of ones. And those, you could have those 3 summation formulas used there. Would be okay, but a little tedious. Ideally, I would like this to just be like n, or just an index. If it was just n squared, I would almost be able to just directly use that n squared summation formula. Um, and something we can do in sums is a redefinition of the index. We can say just let m be n minus 2. Um, Note then that if n is 1, then m is -1. And if n is 5, then m is 3. That means I change the sum. I change every n to be m. So I'm going to start not at m equals 1, but at m equals -1, because that relates to n equals 1, the previous starting index. And I will stop when m is 3. Again, the sort of m value for the final index value of n. And then n minus 2 just is m, so I write that here. That's m squared. Now I'm almost in a position where I can use my summation formula that I wrote for like something squared, a squared term. Except for that formula, I need it to start at 1. It needed to go from 1 to some number. This starts at -1. Well, another thing we can do is just explicitly write out the uh, these extra terms out of the sum. So I write this. The m equals -1 term is, of course, just -1 squared, and the m equals 0 term is 0 squared. And so this is 1 plus this sum of m equals 1 to 3 of m squared, right? Uh, and now this summation, or this really looks like my formula, and I can just plug it in. It's 3 times 3 plus 1 times 2 times 3 plus 1, um, all over 6, right? That was our summation formula for squared terms. And whatever that is the sum of our original sum, or is the value of our initial sum, right? Um, and that's showcasing some of our ideas again, like using substitution within summations, uh, writing out terms from the sum so that you can think of the sum starting from a different index, and then using a summation formula like this. But okay, yeah. So this is just like a little brief intro into summations, formulas involving tricks we can do with it. But hope this helps. Okay.